All right, let's wrap up our discussion and introduction on subspaces and bases, right? So the plural of basis would be bases. Let's wrap this discussion up with an example of how to find a basis for a given subspace and how to extend a basis from a subspace to a total space or a space that contains a subspace. So let's look at an example here. And if you hear a small motor in the back, I apologize, that's my dog down here. Let's consider the subspace defined by V, well, spoiler, V, which is the set of vectors A, B, C, D in R4 such that A minus B equals D minus C. And the question was going to be, is this a subspace? And in my unlimited brilliance here, I said it is a subspace. So let's instead change the example a little bit. Let's show V is a subspace of four-dimensional Euclidean space. How would we do this? Well, what do we need? Let's show V is a subspace of R4 and find, I'm not crazy, you're crazy. We're not trying to show it's a subspace. We're trying to assume it's a subspace and find a basis. Let's find a basis for V. Cool. Now, to find a basis for V, this means we need to, so a basis equals a linearly independent set, let's say a linearly independent spanning set. Spanning set. Okay. To find a basis, we need to find a set that spans V and then make sure that it's linearly independent. How can we do this? Well, one way I would recommend is when you have a set or a subspace described in terms of elements and then some restriction, you always want to see what you can do with that restriction, right? That restriction is really what's dictating the behavior of this space, right? Because this isn't every vector, right? Because not every four tuple or quadruple of numbers in R4 satisfies this criteria, right? And so this is our restriction. And so we want to say like, okay, well, what's special about this restriction? What is that telling us? Well, let's see. If we have that A minus B equals D minus C, well, this means that A would be equal to B minus C plus D. Just add B to the other side of the equation. And then this restriction tells us that for every element of this subspace, we can actually write this with no dependence on A. We can take an element of this restriction out of the picture completely because we have that A is linearly dependent on B, C, and D. So this would be B minus C plus D, and then B, C, D. Now, we need to find a spanning set. That means we need to find a linear combination of vectors such that every vector here can be written as that linear combination. Well, we could write this. Let's first just look at B. Where does B show up in these vectors? It shows up There's one copy of B in the first component, one copy in the second, and then 0 in the rest. And so we know that at least for B, we could always obtain elements of this type by just scaling the vector 1, 1, 0, 0 by B. Same thing for C. It's going to be plus C times, and then where do we see C? We see -1 copies of C in the first component, 0 in the second, 1 in the third, 0 in the fourth. And then the same for D. We see 1, 0, 0, 1. Every element, B minus C plus D, B, C, D, can be expressed as this linear combination. This implies that V is equal to the spanning set of the vectors 1, 1, 0, 0, -1, 0, 1, 0, and 1, 0, 0, 1. Cool. We found a spanning set. How would we show that this is linearly independent? Well, remember, it's equivalent to setting up the corresponding augmented matrix of these column vectors and seeing if when you set it equal to 0, like when you set the corresponding system of equations equal to 0, do we get only the trivial solution, right? That's what it meant. So to check, and let's save some, let's call this U1, that one U2, and this one U3. And we could ask ourselves, is U1, U2, U3 linearly independent? Right? Well, the answer to that question, we need to set up AX equals 0, where remember A is going to be U1, U2, U3, and X is going to be, in this case, it would be like A1. Oh, sorry. Right here, U1, U2, and U3, those are column vectors, right? And here, A1, A2, and A3 are just entries. So this is a 1×3 column vector, right? So, and then the 0 vector is just 0, 0, 0. So what our augmented matrix for this system would be is 1, 1, 0, 0. -1, 0, 1, 0. The third column would be 1, 0, 0, 1. And then we're setting that equal to 0, 0, 0. Right? And so now we would need to put this in reduced row echelon form. And for, to work on new material more, this does in fact row reduce. So reduce row echelon form to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, which gives you that X is the 0 vector, which means this is linearly independent, right? This implies that X equals the 0 vector, which implies linear independence. And so this would show that the basis, so let's just write this out slowly. Since V is equal to the span of 1, 1, 0, 0, -1, 0, 1, 0, and then 1, 0, 0, 1, and that set, I'll just say, again, now I'll refer to them as U1, U2, U3 is linearly independent. A basis for V would be given by 1, 1, 0, 0, -1, 0, 1, 0, 1, 0, 0, 1. Okay, so this is how you find a basis. You have to construct a linearly independent set that spans your entire subspace, right? And that's what we've done here. Okay. You may ask yourselves, well, how do I know that every subspace has a basis? And I won't go over the proof, but we do have a theorem that says every subspace admits a basis. So for all subspaces V in Rn, there exists a basis of V with the dimension of V at least n. Okay, and so we do have that in every case you can find a basis. Cool. Let's see a different example. Let's find another way to find a basis here, right? So here we were given, in this first example here, we were explicitly given this set in terms of a restriction on its elements, right? And we used that to our advantage in finding the spanning set. Well, what if we're just given the spanning set? So let's look at another example. So let's find a basis of W, which is the following set. It's going to be, the following subspace. It's going to be the span of 1, 2, -1, 1, 1, 3, -1, 1, 8, 19, -8, 8, -6, 15, 6, -6. I'm running out of room. 1, 3, 0, 1, 1, 5, 0, 1. Okay, we have a subspace of R4 that is defined by the span of these 6 vectors. And we want to ask ourselves, what is the basis? And here, I can't find the basis based on, sorry for the bad pun, based on some restriction of the set, because now I don't know the restriction of the set. I'm given the spanning set. What do I do here? And since I'm asked to find a basis, I already know it's linearly independent as well, right? So, or not that these are linearly independent, but basically what I'm asking is which of them are linearly independent, right? That's what would give you a basis. So how do we figure out which of these vectors, which of these 6 vectors are linearly independent, and which ones could we get rid of here, right? Because the basis is going to be a collection, or it's going to be a subset of these 6 vectors, right? If our subspace is spanned by these 6 vectors, well, then a basis for it would be a subset of those, right? Because we need it to be a linearly independent spanning set. So basically, just to reiterate, all we're trying to do here is find those vectors which are linearly independent, and then get rid of the ones that are not linearly independent, right? That depend on the ones that are. How do we do this? How to find the linearly independent vectors from the collection above. Here's how we do it. We set up the matrix as we did when we were checking linear independence, right? The first column of the matrix is the first vector you see here in the collection, second, et cetera, et cetera, et cetera. Let's do that. We have the following matrix: 1, 1, 8, -6, 1, 1, and then, but okay, just to be more, this is how you would, kind of the thought process, right? I could just copy my numbers down here. That's fine. You can do it however you want. Let me go column by column so we illustrate what I'm saying. The first vector there was 1, 2, -1, 1. The second vector was 1, 3, -1, 1. The third vector was 8, 19, negative 8, 8. The third vector was negative 6, 15, negative 15, 6, negative 6. The fifth, wait, 1, 2, 3, 4, 5. The fifth vector was 1, 3, 0, 1. The last vector was 1, 5, 0, 1. Okay, I should have picked a smaller example. Now, the process is the same. You need to convert this matrix to reduced row echelon form. So step 1, convert matrix to reduced row echelon form, right? This would take a while to do. We're comfortable with doing that. So I'm going to write down what the reduced row echelon form of this matrix would be. This will be 1, 0, 0, 0, 0, 1, 0, 0, 5, 3, 0, 0, negative 3, negative 3, 0, 0, 0, 0, 1, 0, negative 2, 2, 1, 0. Okay. Once you do this, right, and you should, like for this example, you should take the time to go through this. It took me a while to get this reduced row echelon form figured out, but it's good to keep doing this for practice, right, especially with an exam coming up. This is, I mean, that could be something that shows up on the exam, right? I mean, that's pretty standard practice to take a matrix and convert it to reduced row echelon form. And the more you do it, the easier it gets. So once we have it in reduced row echelon form, step 2 is to locate pivot columns, right? And if you remember, pivot columns are those where you have a 1 as your leading entry and zeros everywhere else, right? As a leading row entry, right? So for column 1, we see that for row 1, the first entry is a 1, and then every entry in that column is a 0. We go to column 2. In row 2, the first leading entry is a 1, and in column 2, every other entry is a 0. That does not apply to the third column or the fourth column, but it does apply to the fifth column, right? And so our pivot columns here are columns 1, 3, and 5. 1, 3, and 5. Then the third step is to take the corresponding columns in the original, or let's say unreduced or unsimplified, in the unsimplified matrix. What are these vectors? Well, we're looking at columns 1, 3, and 5, right? Since we're looking at columns 1, 3, and 5, we take the corresponding columns in the unsimplified matrix. This gives us the following vectors. 1, 2, negative 1, 1. 1, 3, negative 1, 1. And column 5 was, did I say 1, 3, and 5? My apologies. This should be 1, 2, and 5. If you were yelling at your screen, I'm sorry. We have columns 1, 2, and 5 here. And so we take the corresponding columns in the unsimplified version. So that's column 1 is 1, 2, negative 1, 1. Column 3 is 1, 3, negative 1, 1. And column 5 is 1, 3, 0, 1. 1, 3, 0, 1. Step 4. These vectors are the basis. Very cool how that works. And if you'd like to see why that works, I would ask you to read in the textbook where they talk about this. It's section 10.4, I think. I like how they go through another example to see how it works. And so if you're interested in how it works and not just it does work, okay, cool, whatever. If you're interested in how it works or why it works, I would highly recommend you to go read that part of the textbook. So then the basis here, I'll just kind of retroactively, this is your basis for, I think we called the set W. Yep, 1, 2, 3, 4. Yep. And so this is a basis for that set. Cool. Now, let's do a final example here of extending a basis from a subset V to W. Let's say V contains, or let's say W contains the subspace V, and we want to take a basis for V and find a basis for W. Well, how do we do this? Let's see how to do this with an example, because that worked pretty well last time. Let's say W is the, or let's call it V. Let's say this set is the span of the vectors 1, 0, 1, 1 and 0, 1, 0, 1. Okay, so we want to extend the basis of V to a basis on R4, right? You can see V is a two-dimensional subspace of four-dimensional space. By the way, what was the dimension of this subspace that we calculated in the last example here, right? It was in four-dimensional space because we have 4 rows, right? We have 4 by 1 vectors, or 1 by 4. This is a 3-dimensional subspace because remember, the dimension of a subspace is the number of elements of your basis. So we found a 3-dimensional subspace of 4-dimensional space, and the codimension is 1, right? So there would be 1 dimension of freedom to, if you were to try and kind of alter or shape this subspace in some way. Well, we have it here, V is a 2-dimensional subspace, and we want to extend a basis of this 2-dimensional subspace to the entirety of the ambient space. How do we do this? Well, step 1, it's similar. We set up the matrix with columns given by basis, or by the basis of V with the standard basis of R4, all right? We have a standard basis of R4. We want to we want a basis induced from a basis of some subspace, right? These are inherently different. A basis on a subspace is not unique per se, right? There are different representations. So what does this matrix look like? Well, what's our basis for W? Well, by definition, it's a spanning set. And these vectors, it's very easy to verify that those are linearly independent. You can almost do it by inspection. But if you can't, that's totally fine. Set up the augmented matrix, see that you get the trivial. The only solution you get is the trivial solution. Well, so our basis is 1, 0, 1, 1, 0, 1, 0, 1, followed by the standard. I should have said followed by, excuse me, not with, followed by the standard basis of R4, which is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Cool. The next step is to, again, and I'll write maybe like down here, step 2, just put in reduced row echelon form. Now, this is not too tough to put in reduced row echelon form because of all the zeros already. And what you would get, or what I got at least, and hopefully it should be correct, is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, and then 1, negative 1, negative 1, 1, 0, 1, 0, negative 1. Okay. Once you put this matrix in reduced row echelon form, like this, another good practice problem here. And it's still for me, like when I'm prepping these lectures, it's good practice for me to go through these step by step too, right? So what do you do again? We do the same thing. Step 3, let's locate pivot columns. Okay, what are the pivot columns now? Well, 1, 2, 3, 4, like this, right? These are the only columns where the leading entry of the row is 1 and every other entry is 0. Those are the only place that happens. So this is columns. In this example, it's columns 1 through 4. Step 4, take the corresponding columns in the original or unsimplified matrix. What would these be? Those would be, well, it's the basis of V, and then the next two columns, right? Columns 1 through 4 in the unsimplified matrix are over here. So we have 1, whoops. Let's make this a little bigger. We have 1, 0, 1, 1. Get that out of the way. 1, 0, 1, 1, 0, 1, 0, 1, and then 1, 0, 0, 0, 0, 1, 0, 0. Sorry, this should be, they should all be their own vector though, right? My bad. So the first column was that, the second column was 0, 1, 0, 1, the third column, and the fourth column. Step 5. This is the extended basis. Here. Okay, and so this is the extended basis to R4 induced from some subspace, right? And you can see this isn't the standard basis, but it is a basis. And so hopefully now we've seen some good examples that will help you in trying to calculate. Where we're going to go from here is we're going to talk about specific subspaces, like a column space, a row space, and a null space. And these all come from just looking at the column vectors of a matrix, respectively the row vectors of a matrix, and then we'll see what the null space means. And so this gave us a pretty good introduction to some linear algebra here. These are really some important notions of linear algebra.